So let's just finish this question off. So this was the question where you had a particle being let go, basically. So it's a standard sliding down the slope question. There's only one force involved. Sorry, well, no. There's only one force bringing it down the slope, and that's its weight. There is the normal reaction force as well. So let's pop that into a little picture. Here we are. And so we're asked to find the normal reaction force. So I'm going to start by doing that. That's the force of the slope pushing up on the particle. So I'm going to resolve perpendicular to the slope for that. And because it's not moving in this direction, I know this is just up equals down. So the force up, the normal reaction force, is equal to the component of this force. So the angle between that force and perpendicular to the slope is this angle here. And you may remember from yesterday, that's the same as this angle here. So that angle there is theta. That angle there is theta. So that's just going to be 0.5 g cos theta. And they tell us what tan theta is. So if you remember, we know that's 3 and that's 4. So that's got to be 5. So cos theta will be, cos is adjacent to the hypotenuse, that's 4/5. And so that's 0.4 g, which is not a very big value. So we've got 3.92 newtons. Right. So that's the normal reaction force. So you've just got this force pushing up and the component of the weight pulling down. We're asked about the acceleration, and so for that we need to resolve parallel with the slope. And in this case, there's only one force. We don't need to worry about the normal reaction force because that's acting at right angles to the slope, so it has no effect in this direction. But we have got to think about that force there. And the problem we've got is because we don't know theta, this angle is 90 minus theta. 90 minus theta, sorry, on the camera. That's, so if I was using cos, and I know that it's sliding down the slope, so we're dealing with F equals ma here. That's going to be 0.5 g times the cos of 90 minus alpha. And that's going to equal mass times acceleration, 0.5 a. So straight away I'm going to divide by 0.5. The mass has no effect on the acceleration. And this is where it's much easier to say, right, and this was the first thing we did when we started talking about forces at angles. We said that the cos of 90 minus theta was the same as the sine of theta. And some of you who are used to using sine and cos may have gone with that straight away. And going back to my triangle, the sine of this angle is opposite of the hypotenuse, so that's 3/5. So 9.8 times 3/5 gives me the acceleration, which is 5.88 meters per second squared, quite fast. So, you know, if they give you the angle, I'm a happy boy. I can use cos all the time. I'm a big fan of using cos all the time. But when we've got missing values here, it sometimes helps to use sine. And if you can remember that the cos of 90 minus angle is the same as the sine of that same angle, and that's vice versa, then that's all good. There you go. So before we move on from this, let's just have a look at one final example, which is just a little bit more complicated because it's a sort of missing value problem. So we've got in this problem a particle being pushed up a slope. So it's moving up the slope. It's smooth again, no friction. So we've got forces which are acting in relationship to the 30-degree angle, but we've also got the 60-degree angle in there. So the first thing I think it's worth doing is drawing the diagram and working out the missing angles in that situation, and also drawing in the forces which aren't drawn in that picture. So we've got that force, but we've also got the weight of the particle, and they don't give us, and we've got the normal reaction force there. So I can see a number of angles in that diagram that I don't know. So the first thing I'm going to do is work out those angles, and then I'm just going to do my normal resolving parallel and perpendicular to the slope. And I'm hoping that one of those will allow me to show that m is equal to that rather nasty looking missing value expression. So we shouldn't have to type in 9.8 at any point here because we're expected to leave the answer in terms of g. Go on, have a go.
How do you know what to use when, like how you know, like why do you know when it's up equals down, when it's left equals MA?
Okay, the first thing to say that when we're resolving parallel with the slope in these, perpendicular to the slope in these problems, it's always going to be equilibrium. You know, this thing is, these particle questions, they're either stationary on the slope or they're sliding up and down the slope. They're not moving up. So that's always going to be equilibrium. But actually in this problem, that was a red herring. I didn't need to do that. That was a waste of time because I was able to get what they wanted without doing that. Sometimes you need to do both. In this case, I didn't. Parallel to the slope, well, you've just got to read the question. It is being pushed up the slope, so it is moving. And as soon as it's moving, we've got to say, right, is it moving at constant velocity, in which case that's still equilibrium, or is it accelerating? Well, they tell us here it's accelerating. So as soon as we're told it's acceleration, we know we're dealing with F equals ma. And because I'm not very good with negatives, I say, right, which way is it accelerating? It's being pushed up the slope. So that's why, for my forces, I've done the force pushing it up, which is the up component of that force, the force times the cos of the angle between the component and the direction. Take away the down component of this force, which is mg cos 60. But you know, most of us are sort of a week into this, so yeah, don't panic if you're finding it a bit hard. We're going to get lots of practice, I promise you. So I did my F equals ma. That's the 5g force. This is the weight pulling down. That's equal to mass times acceleration. I factorised cos 60, which is a half, and I also eventually read that the acceleration was a half, so that's right, that's a half m. So I can double both sides to get to there. I want an m equals expression, so I get to use my favourite maths technique, don't I? Where I've got two m's, so I'm going to leave the 5g on its own, and I'm going to add the mg to both sides, so I get, I'm then going to factorise, I've still got an a in there, sorry, that should be an n in there, shouldn't it? Sorry, just an n. M plus mg, factorise, and then as required. Okay, so we are dealing with slopes and things moving up and down slopes, and so far we've only looked at one question where there was a friction force involved. So we've now got to look in a bit more detail at friction. So actually we're going to come back to the horizontal briefly. I'm going to start talking about friction. All right. So my demonstration yesterday of friction, this wonderful force, which I can't quite get my head around, is that friction is a force that when I try and push this box and I don't make it move, that's because my force in pushing it is being exactly opposed by this magical force of friction. And if I push a little bit harder but still don't make it move, friction pushes back a little bit harder. And if I come this side and push from this side, friction all of a sudden flips around and starts opposing me in that direction. How does it know? If I am making it move, that's because friction has reached this point where it says, okay, there's only so much I can do. And so I want to talk a little bit today about the before and after of that situation. The before, when friction is exactly opposing me, and then the after, when it's moving but there's still friction, but friction's reached this maximum level. So there's a couple of things that we need to be absolutely clear on. So friction works in the opposite direction to motion, but more than that, it works in opposite direction to the direction the thing is going to move in. So if I'm pushing it in this direction but it's not moving, we say, right, it's going to move in this direction if I man up and push it a bit harder. So friction is opposing that. So friction works in the opposite direction to motion, or the direction, in the opposite direction to the way something is going to move. So it opposes motion even before that motion has started. So if I am pushing from this side, friction is opposing that motion even before I've made it move. And if I push from this side, it flips around and opposes the motion. I'm pushing it, it's not moving, but it wants to go in that direction, and friction is opposing that. Friction has a maximum value. There's only so much resistance that friction can put up as I push that box. And there are two things that affect the maximum value of friction. Firstly, the sort of surfaces that we're dealing with. Okay, so if I rip up the carpet and we've got, I don't know what we've got underneath, a sort of concrete floor, and I pour oil on that concrete floor, it's a lot slippier than it is at the moment with carpet. And if I take the carpet up and replace that carpet with some really rough tarmacy surface, then there'll be more friction. So friction is affected by the surface, but it's also affected by the mass of the thing you're trying to shove. So it's a lot easier for me to push that box on this surface than it is for me to push my filing cabinet on this surface. It's the same surface, but it's a lot heavier. And actually, when we calculate the maximum value of friction, we don't use the mass, we actually use the reaction force, the normal reaction force, the force that the floor is having to push up with. And that's because, there might be other forces involved in the situation. So as well as me pushing it, Callum might be lifting it at the other end to try and make it a bit easier for me. So that would not change the mass of the box, but it would change the reaction because he's helping me by lifting it up. So the maximum value of, and this is sometimes called F-lim, tends to be referred to these days as F-max, is equal to, we use the Greek letter mu This is the coefficient of friction, and that is a measure of the roughness of the surface. And you are nearly always told that in the question. The coefficient of friction is somewhere between 0 and 1. So 0 is smooth, no friction. 1 is stuck. And R, which is the reaction force, the floor pushing up. So those are the two things that affect the maximum value of friction. F equals mu R. So as I said, we're going to return to the horizontal and consider friction in this situation. So we've got a particle of mass 5 kilograms being pulled along a rough horizontal surface by a horizontal force. No angles involved here at all. So should we say it's being shoved in that direction? So if you want to try and label a diagram to show that, including labelling the direction that this magic friction force is moving. So this is my situation here. It's being pulled, and it doesn't say in the question which way, so I've just made an assumption it's going to the right. So friction, I'm using the F to stand for friction, is opposing that motion. It's opposing that motion. Now, we're back to Hannah's question here. Are we dealing with an equilibrium situation here where we haven't yet reached the maximum value of friction and it's not moving? Or have we exceeded that maximum value? So Lewis, are we in equilibrium or are we in F equals ma in this question?
F equals ma.
It's moving, isn't it? It's moving, yeah. It's being pulled along a rough horizontal surface. So we know that it's moving. So the fact that it's moving means that friction has maxed out. Okay? So because it's moving, we know that friction is at its maximum value. And that's a really key point. Because it is moving, friction is at its maximum value. And we can work out its maximum value using mu r. So the first thing I need to do is to work out r, and that's nice and easy because if I resolve vertically, we've got equilibrium, up equals down. So r is equal to 5g. I know that. So, and we're told the coefficient of friction, 0.2. Now I can do that as a separate calculation, or I can build it into my F equals ma calculation. So you've got the option of doing that separately, saying because it's moving I know friction has reached its maximum value, or you can say, right, I'll do it in one go. I'm going to do it in one go now. So we know it's moving, I've assumed it's moving that way. So if we're going to use F equals ma, I've got a 20 Newton force pulling it that way. I've got friction opposing that. It weighs 5 kilograms, and we've got to work out the acceleration. Because it's moving, I know that F has reached its maximum value, so I know that's going to be 0.2 times 5g. And so, you know, I can just type that into my calculator and it will give me the answer. As it happens, in this case, it asks for the magnitude of the frictional force, so it's 9.8 newtons. But if it hadn't asked us that, we could have just built that into that calculation. So because this is already moving, we know what that friction force is. Friction, there's two scenarios. There's before moving, in which case it exactly opposes the force trying to make it move in the opposite direction. And there's after moving, it's maxed out at a value given to us by mu r. How did I know that this was a motion one? Well, we were told, but even if we weren't told, 20 newtons is more than 9.8 newtons. So even if I hadn't been told it was moving, I could have calculated that it was going to be moving because it was being pushed harder than friction could resist. And sorry, I don't know whenever you get to that, so we'll just better work it out for completeness. Divide that by 5, so you get 2.04 meters per second squared. So in this question, we have a very similar setup, another 5 kilogram block, and a horizontal force is being applied. So it's very similar. We've got a different coefficient of friction, 0.4, that means the surface is rougher. But we're not actually told necessarily if it's moving. But we've got three scenarios. So three scenarios here. If the size of this force is 10 newtons, or 19.6, or 30 newtons, what's happening to the block? So the first thing I would do would be to calculate F max. And once I've calculated F max, I know whether in these situations friction was exactly opposing the force and things were in equilibrium, or it was it had given up and we were talking about F equals ma acceleration. Have a go. See if you can work out what F max is and then can see what's going on in each of these three situations. So this time F max is 2g, 19.6. No coincidence there. And so that means that in A, we're not yet yanking this particle enough, this block, enough to move it. So the magnitude of the friction force will be exactly the same as the force being applied. It just cancels it out. And that would be the case for every value up to 19.6, which is the maximum value of friction. So the acceleration there is 0. It's not moving. I'm going to come back to B in a minute. For C, we're now shoving it hard enough. So we're now into F equals ma. Okay, so in C, we are pulling it with 30 Newton force. Friction is going to resist that, but it's only going to be able to resist it up to 19.6 newtons, its maximum value, and that's going to be equal to 5 times the acceleration. So in part C, the force of friction is 19.6, that's its maximum value, and the acceleration is whatever that calculation tells us. So we come back to B. B's really interesting. I mean, what's going to be happening if this force is exactly 19.6? Is it going to be moving, or is it not going to be moving? What do you reckon, Calvin? Is it moving or not moving? And can you justify that?
Because the forces will still be equal.
Yeah, we've got a 19.6 Newton force pulling it, and friction resisting it with 19.6. So this side of my F equals ma will be 0, so acceleration is 0. But this is a crucial point. Have you done this in physics? This point here is referred to as limiting equilibrium, or sometimes limiting friction. This point here is when this block is about to move, and it's a really good point to use because nothing's moving yet, so everything's really, really simple, but we know that friction's at its maximum value. So what we're dealing with in part B is a situation that's referred to as limiting equilibrium. It's about to move, we are about to exceed the maximum value of friction, but we haven't yet reached it. And so in that case, friction is 19.6 newtons and the acceleration is 0 because it hasn't yet started to move. But we will come back to situations that say the particle is in limiting equilibrium or similar sort of wording. We're dealing there with a situation where it's about to move. Any more force is going to create an acceleration, but not at the moment. Not yet at the moment. So I'm a huge fan of friction because I think it's so clever. So let's just. Sorry, I'm trying. So here's a little sort of selection of questions where we've got to say what state we are in. Are we in the before limiting equilibrium state where we haven't yet reached F max, in which case friction is just exactly opposing the force and acceleration will be 0? Or are we in the after state where we've exceeded F max, so we are now accelerating? And the first few are quite straightforward, but then when you get to D, it gets a little bit more complicated because you've got other forces acting vertically, so R won't just be equal to 5G because you've got other forces involved there, and if R is different, it means that F max is different. Coefficient of friction is 1/7, so that won't be different. So I'm hoping that we can see this. It's on page 103. So if I give books to people at the back, can you see that, Laura? That's page 103 for those at home. This is obviously in the Pure 2 textbook. So your value for F will either be exactly the same as the force acting in the opposite direction, or it will be its limiting value. Yes? Yes, Kushka.